we'll introduce a little bit of notation here. V bar, we read this as V bar, that's V with a bar over it, is what we call average velocity. If we put a bar over a variable quantity, we generally mean an average value of that quantity. So V bar, average velocity. We know that average velocity is average rate of change of position with respect to clock time. I didn't write the whole thing out. And that's change in position divided by change in clock time. And if we denote position by x, then the delta x stands for change in position, delta t stands for change in clock time. So that V bar equals delta x over delta t. And similarly with acceleration. Average acceleration, A bar is average acceleration, which is an average rate of change, etc. And by the definition of rate of change, that's change in velocity divided by change in clock time, which we'll write delta V over delta t. As above, we've looked at how the definition of average velocity leads to the definition of instantaneous velocity, velocity at an instant. And we'll do the same thing here. Average velocity is delta x over delta t. So velocity at a clock time t is going to be defined to be the limit as delta t goes to 0 of delta x over delta t. Now that's really not a very specific expression, but we make it specific in the next step by saying what this means is the limit as delta t goes to 0 of x evaluated at t plus delta t minus x of t divided by delta t. The difference quotient, the standard difference quotient that you studied in first year calculus, and the limit definition. And of course, that means that if x is considered to be a function of t and velocity a function of t, that the instantaneous velocity is a derivative of x of t with respect to t. And we can say the same exact thing about acceleration. And we come to the conclusion that the acceleration is the derivative of v of t with respect to t.